All right, another example of direct comparison test. We're going for it here. N equals 1 to infinity, 1 plus n to the third over n sine squared of n. Wow, that's awful. It's pretty common that if you see something really awful, maybe pretty common's overstating it. Let that be a trigger that maybe you should compare it, because when you compare, you end up getting rid of certain aspects and you boil it down to something much simpler, right? So 1 plus n to the third over n sine squared of n, man, there's a lot going on there, right? I don't want to use integral test, take that antiderivative, right? Certainly it's not a geo or a p series or a telescoping, right? It's not any of those things. Um, so let's check it out with direct comparison test. Okay. So I'm going to begin just by kind of putting it out there. What is bad about that integral? Like, what's in the way? And we've seen a lot of like adding 3, subtracting 1. Those things are easy to clean up and then compare. So I think that 1 plus in the top, we could get rid of the 1. But probably what's really kind of a hindrance here is this sine squared. Can we get rid of sine squared of n? And yeah, that's the way I'm going to start. I would recommend just get rid of one thing at a time. And maybe you do multiple steps in your comparing, but I'm going to just start with this. So I'm going to take my original series and I'm going to get rid of the thing that's really awful, the sine squared n. We'll then do another step where we get rid of the 1 plus. But one thing at a time, because we don't want to goof this up. All right, so if we remove the sine squared n, what does that do? And you're like, wow, I have no idea. Hey, wouldn't you agree that sine squared of anything, well, it's going to be positive, right? And it's going to be less than or equal to 1. So we are removing something that is somewhere between 0 and 1. And I think we're assuming there's no value of n that we'd plug in to give us 0 and make us divide by 0. That would be like a pi or something, right? Which is not going to happen. Okay. So maybe we can really say, we could probably, in this case, we could really say that. Okay, so it's somewhere between 0 and 1. Well, if that's there, then when it multiplies, it would make that denominator smaller. So if we get rid of it, now the denominator is bigger. If the denominator is bigger, then the whole thing gets smaller. All right, that makes sense. Now I'm going to try out getting rid of the 1 in the numerator. Let's see. And it's got to keep going the same direction, right? Let's see here. If I get rid of the 1, then now the numerator is smaller. And I don't have to do this kind of backward sort of logic like a denominator. The numerator got smaller, so it's smaller. Hey, this is great. So this is definitely smaller than that. And this simplifies really nicely. N squared. Okay, so we have compared it to something very simple, and we know the relationship. So far, so good. Now, once we have our new series, of course, we need one of our previous tests in order to figure out what this is, and then hopefully it will fit the way we like and we can answer for the original. But in this case, what would we really desire this to do in order to have an answer to the whole thing? We need this to diverge, right? Because it's the smaller one. The smaller one diverges, the bigger one diverges. And it turns out it will. Maybe you saw that already. Hey, n squared. Well, sure, of course, it's going to add up to infinity. But we can't just say that. hey, everybody, obviously this diverges. No, that does not work in math. We have these theorems. Everything's based on theorems that everyone has agreed upon. We need a definitive test. We can't just say this obviously diverges. We got to have a test. Well, what test applies there? Actually, there's one test where all it does is show things diverge, and it'll work here. Maybe you know what I'm talking about. The divergence test. Hey, if we take the limit of this guy, n squared, as n goes to infinity, well, we get infinity. Hey, does infinity equal 0? No, infinity does not equal 0. So we can tell that this series right here diverges by the divergence test. We've done it. We've shown that diverges. Sure, it was obvious, but we need that formal test. So then we can say that original series, and being very clear what I'm talking about, right? Recopy it. It diverges by the DCT. This was horrible. Oh, what an ugly series, but with a couple of comparisons, boom, boom, a simple test, done. Comparison test, very powerful. Very, very powerful. And you really like, when I'm doing this sort of thing, like get greedy. You know what I'm saying? Like, I want that sign squared in, gone. Like, let's just get out of here. Okay, gone. Now what changed? Man, let's go further. I want that 1 plus out of here. Okay, gone. How did it change? And what do you know? It just fell right into place for us. Okay, you may be thinking, what would happen if, say, we did all this and logically it all worked out the same way at the top? What if that new series had not diverged, right? If it played out a little bit differently. What if that had actually converged? Could we say something here? No. If this diverges, we know this diverges. But if this converged, we would not be able to say anything about the original. If it was always getting smaller, right? Hopefully you're following that. So we got really lucky that this diverged so that we can answer this diverges. But if this converged, man, we'd be in a tough spot. Luckily, if that ever happens, if the thing that you're hoping to happen doesn't, we've got another comparison test called the limit comparison, abbreviated LCT. Looks like I scribbled something out there and rewrote it. So ignore whatever that scribble is. Okay, I'll give you a moment to copy this. A trash truck just drove by me. Don't know if that came through on the microphone. I imagine it did. Okay, here we go. Limit comparison test, LCT. If a sub n is greater than 0 and b sub n is greater than 0 for all n, so we're saying they're both positive. That's got to be true for any comparison test. Everything's positive. And the limit as n goes to infinity for a sub n over b sub n equals L. So we're taking the ratio and then applying a limit to it. And it equals L, okay, where L is greater than 0 and finite. So now L has to be a positive number and not infinity, greater than 0 and finite. If that's all we show, then we know that the two series, the one for AN and the one for BN, do the same thing. Either they both converge or they both diverge. Now that is really powerful. And you notice we're not even comparing AN and BN, like which one is bigger, which one is smaller. We're just saying if you've got these two series and you take the limit of this ratio and you get a number that's greater than 0 and finite, then you know they both do the same thing. So if you can say something about one, then you can immediately conclude the same thing about the other, or vice versa. Just so a really quick explanation of why, well, obviously we're not going to prove this test, but just kind of think to yourself, right? So if they, what if they weren't the same, I think is the best way to go. So what if, A diverged, but B converged? That diverges, that converges. Then when you take this limit, if that's diverging and that's converging, then your answer is going to go to infinity. And we're saying, okay, just be sure that doesn't happen, right? Or if it was the other way around, what if this converged and this diverged? When you take that limit, converge, diverge, well, then the infinity's in the denominator and this limit's going to go to 0. And we're saying, well, it's not 0, right? So if when you do this, you don't get 0 and it's not infinite, then either it's converge to converge comparison, or it could be a diverge to diverge comparison, and they just happen to cancel out. Okay. Anyway, I think that's enough explanation. Let's get to an example here, and I told you guys you'll know to use limit comparison when your comparing doesn't work out the way it should for direct comparison. So always attempt to use direct comparison test first, and then if the logic is backwards for the inequality, then you know, okay, that didn't work. I'm going to fall back on limit comparison. So here we go. We got a good one. N equals 0 to infinity, 3n plus 1, 3 to the n plus 1 over 4 to the n. Okay, this is a nice one. It's even going to fall back on some of the, any comparison test uses a prior test as well. So let's see. 3 to the n plus 1 over 4. What would be really great to get rid of? And I think, well, man, that again, it's like the plus 1 is pretty common. Like if we get rid of that plus 1, then I'd have 3 to the n over 4 to the n. I could think of that as 3 over 4, all raised to the n. And, well, maybe that's not as obvious as I thought. Let's just get rid of the plus 1. Apply DCT. Okay. So here we go. And I filled in these parts for us since we've thought about it a couple of times now. If I get rid of the plus 1, then it becomes 3 to the n over 4 to the n. And okay, I see that this one's bigger, right? Getting rid of plus 1 makes the numerator smaller. So this is smaller than it was before. I've got this is the greater than, this is the small, okay. This is the bigger one. Why would I like to get rid of the plus 1? Because then I can think of it as 3 over 4 to the n. Why is this nice? Because that looks like this. That's a geometric series. And in fact, it converges, right? And the absolute value of r equals 3/4. It is the 3/4. That's less than 1. I know geometric series converges. And I've kind of off the screen the geometric series test right there. And if I'm pointing to the series with an arrow, then it's clear which one I'm talking about. Okay, so I've compared, and I know this converges. But wait a second. Is that what I wanted? This is the smaller. The smaller one converged. I have no idea what the bigger one does. Oh no. Had this diverged, I would know it. But it didn't do what I wanted. Okay, so DCT, not going to work. So I'm going to fall back on LCT. Oh no, yeah, there's the test. Converges, but the original one is bigger. Oh. So I'm going to apply LCT, and here's how it's going to work. I'm going to think of the original series as AN. I'm going to think of the new series that I attempted just now as the BN. So once I apply or attempt DCT, if it doesn't work, I've already set myself up perfectly for LCT. So I've got that as my original. BN is the new one, and I'm going to go back to thinking of it this way because when there's my notes, right? The original, what I tried with DCT. And I think I need to go to the next page. Maybe I'll try to keep this kind of flowing. Okay, there you go. So then I put them in ratio, right? AN over BN. And if I can take this limit and figure out if it converges or diverges, then I got it. Okay, so what's nice, because I only changed the +1, I'm going to get some nice cancellation. Right? I'm going to flip that denominator and multiply, canceling 4 to the n. Once those are gone, then I'm looking at this. And okay, limit 3 to the n plus 1 over 3 to the n. How did I attempt this? I'm going to look down at what I tried to do. This is really nice. I suppose you could apply L'Hopital here, right? Because you've got infinity over infinity, and you could do those derivatives, and that would be just fine. Or you could realize, hey, isn't this 3 to the n over 3 to the n plus 1 over 3 to the n? And that's how I thought of it. Just split that denominator. That makes the limit a lot easier. The limit as n goes to infinity, well, that's going to go to 0. So this is going to equal 1. And we just need to make sure that our answer is not 0 and it's finite. If our answer was 0 or if it was infinity, then we'd still be stuck. We would not have an answer. But luckily, we had a nice comparison. We had set ourselves up really well so that this all came out. And the limit equals 1. That's a positive number, and it's finite. So we know that both of these do the same thing, right? I mean, if we go back here, after this limit, I know these do the same thing. Hey, do I know what one of these does? Yes, because I already figured this one out when I tried to do DCT. I mean, oh my goodness, I've already done all this work. I already know that that converges by DCT. So now that my limit worked out to equal 1, I can say that this one does the same thing. I know that now both series converge or both diverge, but that new one converged. I already showed it. So I can say that the original 3 to the n plus 1 over 4 to the n, starting at 0 even, converges by LCT, the limit comparison test. And there you go. Now, I know we've gone kind of long on this video, just the nature of these problems. There's a lot of steps to them. Again, the moral is try DCT first, and if the logic doesn't match up the way it should for DCT, fall back on LCT. You've already done the hard work, if you will. You just got to take that limit. Of course, LCT is a test independent of DCT. You don't need to start with DCT to use LCT. It is a test all on its own. So, if you see a comparison and you want to just jump right into LCT, you certainly can. There's nothing wrong with that. I find, though, that I would much rather DCT work, and I use it as a fallback. But it is a standalone test and is quite powerful just going about it that way. Okay, that is the end of 11.4. So bring concerns, questions in the lecture, homework questions to our Zoom meeting time. See you there.